Hello, this is Dr. Asan Abdullah with the course Deep Reinforcement Learning, and we are covering the topic of reinforcement learning. And this is topic number 10 in the list of topics which are covered in this course. And the subtopic is D. So the difficulty level is high for the content covered in this video. And this video has the supplemental website, which is accessible and available at www.ezmcq.com /goget, and which is a personalized learning management system. So, what is the future of content delivery? So the future of content delivery is delivering the content online, and the wonderful features and the benefits are in front of you. And this approach is used by hundreds and tens of millions of users worldwide, which use content delivery for the learning purposes, for education purposes. And we are going to be following the same approach in this course also. So in green color is the URL for the personalized learning management system, and in blue color are the videos which explain the features of the personalized learning management system with reference to the future of content delivery, which is as a matter of fact the present. So what it supports is advanced and basic text search in the content of the course coverage, which is not there in very popular learning management systems. And then, of course, if there are any students with visual disabilities, they can also change the font, the color, the line spacing, etc., to suit them to their requirements, which is also not there in leading learning management systems. And then all the content is kind of opens up and unrolls so as to optimize the small screen of a handheld smart device. And you can also track your progress, what you have covered, what you have to cover. And of course, you can also test yourself online in real time about the knowledge assimilation and the knowledge which you have acquired, and the weaknesses are also identified. So, what is the approach of content delivery? So, there are two approaches. One is the question and answer based, which is proactive, which is engaging, and which is also promotes thinking also. And the other approach is the traditional approach in which a lot of details are provided. So, the approach we have adopted is a blend of both approaches, that is Q&A and traditional learning also. So this is the list of topics which are covered in this course, and we are at topic number 10, which is reinforcement learning. So this is the breakdown of the list of subtopics or the concepts which are covered in this video or in this sets or series of videos. So 10A in yellow color are the basic or the fundamental concepts of reinforcement learning. And as we proceed from A to B and so on up to E, the difficulty increases progressively. And for the video lecture 10E, we have the more challenging concepts. And now we move on to the details of the video. So we are at lecture 10D, how to play a tic-tac-toe game uh, using reinforcement learning through neural networks. Okay. So what we are looking at is we need to, first of all, we need to define the environment, because we need to map the problem so that it can be worked with and or executed in a required environment. And then, of course, that has to be mapped to, or there has to be a corresponding neural network architecture. And then is a training process. So before we jump into this, let me give you a little bit of background, because this involves defining the game environment. And how is that defined? By that has to be defined clearly by specifying how the states are represented, how the actions are represented, and how the rewards are represented. Okay, so then of course the neural network approximates the Q function, and it also predicts the expected future rewards, and how it is done for each possible action based on the current board state. So the training uses deep Q learning. And how does this works? The agent learns by playing the game and by storing the corresponding experiences and updating the network through, say for example, mini batch sample from the memory, using the memory. So the use of a target network uh, help stabilize the training. So what happens that as the agent plays, okay, so over the period of time, the agent improves. How does it improves? By which we always discuss for reinforcement learning, by balancing exploration of new moves and exploitation of the known strategy. And eventually, finally, the agent learns to play tic-tac-toe optimally, or of course, near optimally. So this approach leverages the neural network's ability to generalize, okay, and using the remote learnings, I'm sorry, using the reinforcement learning's trial and error framework. So if we first of all let us for example try to look in more detail uh, at this diagram. So we have this board, and the board has nine positions, and they are the columns have alphabets uppercase, the rows are numbers. So column and so cell A1 has one, which is representing the cross, and B1 is -1, which represents the zero, and the empty cells A2 is zero, okay, and empty cell A3 is also zero, and so on. So here we have the neural network. So this is the input, and this is the output, and of course, as you can see that this output 0.998 that has the highest value. So if we look at the details, so we need to define the environment. So there has to be a state representation, which I've already discussed, okay, and then we have the how to represent the actions. So the what are the actions? Basically, the actions correspond to the nine possible moves. What are those moves? Those moves are placing an X or a zero in any of the nine positions to begin with. And then, of course, as we proceed, the number of positions where we can place X or zero, they reduce. Now there's a reward function. So the rewards are defined based on the outcome of the game. So win is +1, lose is -1, and draw is 0. So what is the neural network architecture? So the input layer, we have nine neurons. We have nine neurons. Okay. This is one, two, three, four, five, six, seven, eight, nine. So we have these nine neurons, one for each position on the board, because there are nine positions. Then there are hidden layers, one or more hidden layers, because we are not looking at a deep learning solution. And with the ReLU activation functions. Then we have the output layer, which this is the output layer, which again has nine neurons, and each representing the Q value for placing an X or a zero. So then is the training process. This is the training process. Training process. Okay. I'm sorry about that. It's not coming here. So we have this training process, and in this training process, first of all, we initialize the neural network with random weights. Okay, and then we initialize a target network. What is the target network? That will be used to compute the target Q values for to ensure stability also, and so on. So then is the experience replay. So what is experience replay? We store the transitions. What are the transition state, action, reward, next state into a replay buffer. And then what we do is, then we do a sample random mini batches, which we've already covered, okay, from this buffer, and we try to break the correlation between consecutive experiences, right? And then we have the training loop. So what do we do in the training loop, or which is here like iterate the training loop? So we initialize the game state, and then we select the actions. Actions are which cell we want to go, and use the epsilon greedy strategy. What we are trying to do is balancing exploration and exploitation. Then we take an action, observe the reward, and transition to the next state. Then these are the experiences. So we store the experience, save that transition in some buffer, and then we sample the mini batch, right? And we update the Q network. I'm not going to a lot of details. Okay, so there are a number of things we need to do, right? Now, if we go into further detail of the training process, so there are periodic updates to the target network that help stabilize the learning, right? So there's not much more detail here, but the purpose of this Q&A was to give you an idea that there can be a matching. Okay, there can be a matching of how tic-tac-toe can be played using a neural network. So we move on to the next Q&A, which is this is more interesting. How reinforcement learning can learn optimal strategies to play against an opponent. Okay, so I will explain this. So basically, what this diagram shows is that this is the our move, okay, and this their move. So so we take turns. So one of them could be the agent itself, right? And then based upon those moves, there is either a win, or there's a loss, or there's a draw also. Okay, so this is how this is taking place. So what is happening is there. Uh, so this how this the learning takes place, or the optimal strategies are developed. They stem from the iterative trial and error process, which we refer to the Napoleon's approach also. And this is guided by the reward signals. So it is guided by the reward signals because it is delayed reward. And those guided reward signals reinforce successful action. Okay. Now what happens that this is a continuous improvement process, and through this continuous improvement, the agent uh, develops the policies which are increasingly effective because the experience is added to that. And not only the experience, but there is a balancing, okay, between exploration of new moves and exploitation of the known tactics, or the known moves. So this balance basically avoids suboptimal traps. What is a trap? Getting stuck at a local minimum. And that also, now this, when this is avoided, those suboptimal traps are avoided. That ensures that the agent can adapt to varying scenarios. So what we are looking at, reinforcement learning's capacity to implicitly model, right? And now what we're trying to model, uh, opponent's behavior and respond to opponent's behavior. So what it does, it enables dynamic strategy adjustment, because if there is no dynamic strategy in adjustment, then that's a recipe for a failure. So what this does, it provides robustness against not only unpredictable opponents but also against diverse opponents. So whatever that agent is doing together, these elements form a learning framework, and that framework can also generalize well. So what is a consequence that makes reinforcement learning highly suitable for adversarial games, for complex games, and where opponents' strategies are continuously evolving. So so the opponent is ensuring that uh, the agent finds it is more challenging for the agent to learn. So if you look at more details, so with reference to trial and error, okay, what is the benefit of trial and error? This allows the agent to explore a wide range of action and observe their consequences also. Okay, because actions have their consequences. Now, foundation, uh, this uh, this foundational mechanism mimics human learning, which is the key to which is what we call as artificial intelligence, and it enables the agent to improve decision making. And how that decision making is improved, it is through experience. Okay, so what the agent does, that the agent systematically tests different moves, like burning the hand, like falling in a ditch, okay, and learn from those mistakes. That if something is glowing and it's hot, stay away from it, okay. And the agent builds an effective policy without needing explicit instructions by human intervention, or by manual process. So what it does is that it ultimately discovers successful strategies autonomously. So this is like a child, okay? A child might find a glowing coal very attractive, okay, or a glowing ember very attractive, and when the child touches it and burns their hand, then they make a note that to stay away from such things. So so that is autonomous learning. Then is the learning from rewards. So there was a penalty, and then there can be rewards also. So those rewards act as a positive feedback. Positive in the sense that that reinforces good decisions. So not only good decisions are reinforced, but poor ones are discouraged also. So the reinforcement learning agent's goal is to maximize the cumulative rewards. Okay, and what this does is it shapes its behavior. Okay, and to like favor certain actions, which actions that lead to success. So we have a reward driven approach. Learning from rewards, we have a reward driven approach, which what it does, it enables the agent to identify which strategies yield better long term results, and the policy is updated, right? And that guiding policy is updated, and how that guiding policy is updated through positive and negative reinforcement, both. And of course, then we look at how this improves over time, how it improves over time. So this is an iterative approach. So this iterative policy, it is updated based upon the accumulated experience. Those experience could be good, those could be bad also. So what the agent is doing, that it continuously refines its action value estimates. And what it does, that it enhances the agent's ability to predict the outcomes of the move based upon the prior experience. Now, this is a gradual learning experience, and that learning process enables adaptation to, of course, complex and changing environments. And what it does, it allows the agent to develop a complex and sophisticated strategies also. All right. So again, we cannot like there always has to be balance. When we are talking about reinforcement learning, we have to take into consideration exploration and exploitation. So there has to be a balance between exploration and exploitation. Why? So that ensures that the agent neither gets stuck at a local minimum using known strategies, nor waste too much time and effort on making the moves that were not made earlier, that is unproven moves. So obviously exploration helps discover new tactics, while exploitation capitalizes or leverages the best known strategies. But there has to be a trade-off. So what effective algorithms do is that they dynamically manage this trade-off, and that facilitates comprehensive learning. And when the learning is comprehensive, then the performance is efficient. And lastly is adapting to any opponent. The agent learns to anticipate as the agent accumulates experience. The agent learns to anticipate and counter opponents' moves by modeling their behavior through the interaction. Now, then there's also the dynamic strategy. Now, adjusting that dynamic strategy based on the observed patterns allows the agent to generalize across diverse opponents. As we see here in this diagram, right? So we see that the agent is playing against an opponent, right? And makes the adjustments also and generalize also. So this is an adaptability. So this adaptability makes reinforcement learning robust in competitive environment where the tactics of the opponent can vary or evolve. Now I'm again quoting the quotation of Napoleon that the opponent, so to be successful, your strategy should vary and should evolve. Otherwise, your opponent, your adversary, will learn your art of war and will succeed ultimately. Okay.